Sorry, I was clicking the wrong. Okay, so good evening, everyone. My name is Saida Said, and I am a research scholar at IIT Roorkee, and this is a part of the TAship program for PMRF, and we will be going over the course of Soil Mechanics 1, and these sessions will be for like understanding or developing an understanding and some problem solving based on the week's content of the excuse me course. So first we will go through what has been covered this week in this session week. Okay, so this was the week one. This course is by Professor Dilip Kumar Bedia. So this is just an overview about soil mechanics and what's the difference between studying soil as a science and studying it as a technical subject like what's the soil technology and soil science. Dif- Difference between soil technology and soil science. So basically, we can say that when we go into the technical so when we go into the technical field, we are more about quantification of the processes, while when we are talking about soil science, it is more or less qualitative or less quantitative, less rigorous. Um, so this is the rock cycle. This is what you have covered in this week. Sedimentary rocks, metamorphic rocks, formation from rocks, what is transported soil, and what is residual soil. Residual soil is the soil which is not transported by any transporting agent like wind, water, or air, or gravity. There are four types of transporting agents that can, after disintegration of a rock into formation of soil, it can be transported through water. If it's transported through water, it will be called alluvial deposit. If it's transported through air, it will be called aeolian deposit. If it's transported under gravity, I believe it's called colluvial deposit. And if air, water, gravity, etc. Okay. So Lewis is transportation by wind, residual soil, laterites. So this is just a very, very general introduction. If you see here, up till now, we are talking about very qualitative things. Like it's not something you can put a number to and give a unit to. It's not quantitative. But when we move towards the quantitative, uh, when we move towards this quantifying properties of soil, we talk about permeability. Like permeability is how much water or fluid, how much resistance your soil matrix shows to flow of water or fluid through the matrix. Compressibility is the permeability was the resistance to flow, while compressibility we can think of as a resistance to deformation. How like what we do usually in solid mechanics is we define moduli, we define an elastic modulus, we define a bulk modulus, and that is the same with soil also. What we do is we try to quantify the stiffness or the strength of soil by um, defining either moduli or other parameters, uh, and then shear strength. So this is one of the most important uh, topics for soil, because if you see, if you think of it, let me connect my pen. Just give me a moment. Just disconnect now. Um, so what we will do is we will uh, split the screen so that we have a working surface here, working interface here. Okay. Yeah. Shear strength, if you see, if you try to uh, visualize it, if you have a soil matrix, so soil has no tensile strength. You can think about it this way. I don't think there is any kind of soil which you can pull on both ends and it will not very easily break, unless and until it's a rock or it is a very hardened clay. It is assumed soil has almost, it has 7 dyne per centimeter square. I think tensile strength is very low. Compressive strength is high, but usually all the failures in soil take place. They're not because of compression, because you see, soil, even if you compress it, it's not going to cause that much an issue, and it has good compressive strength. Mostly failures take place in shear. If you have a foundation here, so what can happen is, if there is a shearing failure, that there is a shear plane that is developed, this kind of a failure surface can develop, and then soil can come out from here, and this foundation can sink in like this. So this sharing, or when you have a slope, this kind of a landslide or slope failure occurs. This failure, along in which the forces are acting in opposite directions as shear surfaces, these are shear failures, and this is the most important topic uh, that we want to study about our soils, because whenever you construct something as geotechnical engineers, the most important thing that you uh, determine first is the bearing capacity of the ground on which you are constructing anything, be it a road, be it a building, any structure in the world. Nothing is in air, everything is on the ground. And when you're constructing, the first thing you want to know is what is the um, strength of this soil. And when we talk about strength, how do we quantify it? We quantify it as the shear strength, because that is the most critical. Then, so initial, if we talk about initial, like an introductory thing is, first, if you go on a field, as a field engineer, you go to a field and you have been asked to analyze the soil there. The first thing you will do is visually analyze the soil and try to understand what kind of soil it is. And this brings us to index properties. So this brings us to index properties. Index properties are like properties that you define for a soil to identify it. It's like a characteristic. For example, you go to your blood bank and they tell you that you have an A positive or a B positive blood type. So these are some properties how we quantify. First of all, using these properties, we have made groups, different types of groups for soils. And then we have taken these properties, given some limits, and then defined that if property A is between L1 and L2, then the soil type is this. So that is called, uh, this is like, this is called classification of soil. So why do we classify soil? Usually, how we classify soils, we classify soils as coarse grained, then fine. Coarse grained can be gravel, then it can be sand, and then we have fine grained, which are clay and silt. So why this classification is needed, first of all, is because all these soils, types of soils, they behave very, very, very differently than each other. Even though we can say that all of these are soils, they are a subset of a broader um, uh, this thing we can call soils, but they behave very differently. If you see gravel, you think about it, if you put water on a gravelly path, it will just dissipate. It will just not dissipate, it will just flow through because it has a very high hydraulic conductivity, high permeability for water. But if you do the same with clay, it's going to stay on the surface for a longer time because the permeability is very low. And strength characteristics, permeability characteristics, compressibility characteristics, they vary very much between these. So that is why we need to classify, even if it is, for example, let us say that I have a sand, I can have two very different kinds of sands. So let us say that one of my one okay. So let us say that one of my samples has similar size particles. Other sample has varying size particles. Okay. So what do you think the packing of this soil will look like? The packing will be very loose because all particles are almost same size. So we will have greater voids, greater number of voids here. But the other soil, even if you have these particles, you may have some smaller particles that have that are occupying the voids. So this is called a well graded soil, which has particles of, we will talk about this a little. Yeah, you must have studied about this gradation of soil. So if the diameters of particles, if this is the diameters of particles, the soil has a range of diameters. All these diameters are present. This diameter is less, this is more, we can say. But this kind of soil will either look like uh, so the poorly graded soil will either look like this, in which you don't have enough of this range of particles, or it will look like uh, this. So all these particles are missing. So, in these kinds of soils, their properties differ from well-graded soil properties. And why is that? Because everything boils down to the particular nature of soil, what kind of a structure the soil skeleton is forming, and based on that, its permeability, its void ratio, its strength characteristics, all of this will be affected. And that is why we need to identify, first of all, when we go to the field, first we will do the visual identification, as in visually, is this gravel, is this sand, and then we take the sample, and then we do all these tests for identifying the soil using index properties. Index properties are the properties, as I was just saying, that are used to classify the soil. So first index property we can talk about for sands, for example. Sands, first of all, we have particle size curve that we try to plot for the soil. Then we have um, a classification system and limits for sizes. For example, if the size is greater than 4, yeah, if the size is greater than 4.75, then this is gravelly soil. If it is between 4.75 to 75 micron, it is sand. Then less than 75 micron to 2 micron, you have uh, silts maybe or clays. Mm, this is not usually based on the mm, grain size, but cohesive properties. It is like we cannot say that uh, the size is this much, so it will be clay. The difference between silty and clayey will depend on the other index properties. These are the index properties for the coarse grained soils. So, what are the index properties here? In your grain size distribution curve, you will take the diameter D60, D10, maybe D30 also, and then you calculate Cu and Cc. So this is the diameter uh, below which 60% of the 60% of the uh, particles are finer than this diameter. Okay. So this is how we do the sieve analysis. We take these sieves and we just put the soil here, close, like form a column of this, and then we shake, and then we calculate the weight retained on all these sieves, and then we calculate the cumulative weight, and then we subtract it from 100, and we will get the percentage finer than. This is the particle size distribution curve that I was talking about. We have gravel here, we have sand here, we have silt here, and we have clay here. So this is a well graded soil which has almost a long range of uh, yes, ARV. Arav? Yes, Arav?
Well, yeah, good evening, madam.
Good evening.
ARV, madam, it is not Arav. ARV.
Okay.
A small doubt, madam.
Yeah,
Good evening, madam.
good evening.
So, what is the doubt is soil classification. Nowhere it is mentioned that it is for natural soil or blended soils.
Okay.
Because whatever you are giving in IS classification, we have a gravel, sand, silt, and clay. Only four terms,
Yeah,
along with the subgroups of whatever may be.
yeah,
For example, in your research, or maybe in most of the research work, nowadays the people are using the industrial byproducts
yeah,
like fly ash or something else.
yeah, yeah.
Now, can you show me the table, madam, just before this graph? Table you have shown. Here, pan, the material retained is 7.24 grams. That means it's indirectly silt and clay.
Yeah,
Yes, no, madam.
yeah.
For this soil, for
11.04.
example, if I blend,
Yeah, yeah.
no, madam, it is pan at the
Yeah,
receiver
yeah.
bottom.
I'm trying to see the cumulative weight. Okay. So
Okay, now it is
95%,
7.4
there is
grams.
only 2.41 percent finer than 75 microns. So this is like sand.
Not that, madam. Not that. Pan, weight of the material retained on the pan.
Yeah.
7.4 grams.
Ah, 7.24
Uh,
grams.
this is this is if we assume soil is a natural material, then this 7.24 is a silt and clay together.
Yeah.
Now my question is, if I go for some stabilization or modification of soils with the blended material, let us take example of fly ash. I am going to add a 50% of the total soil I have taken.
Okay.
I will add 50% of soil and 50% of fly ash, blended
Okay.
material for my
Yeah.
research work. Then automatically the material retained on the pan becomes very high.
Yeah. But you have to understand this first of all. Uh, uh, First of all, when you are mm, doing research, I have also worked on industrial byproducts. I have worked on red mud. I worked on recycled concrete aggregate. I have worked on recycled asphalt pavement and some more. My field of research is geoenvironmental engineering. So that is why I feel comfortable in discussing this. So the thing is, these uh, classifications that we are given, if you read these research papers, uh, they kind of take this frame of logic that we have developed for soil, and that is why we call this geo-environmental engineering, because we are using the um, uh, we use the concept that we developed for soils, and then we are extending them or extrapolating them to um, uh, other granular materials, particulate materials that may show same properties. Now it is a it is it is the researchers' judgment based on the researchers. One second. Okay, it is based on the researchers' judgment how you go beyond this, because this is like hand holding will be done only up till soil. After that, when you go to the research part, you will have to choose. You have to. Uh, that is the research part, that you have to think about what you are doing and think about up till how much. What is the limit to which we can take these soil properties as it is, and then after that it may not. For example, if you talk about fly ash, fly ash is the pozzolanic substance. Uh, there are studies of soil stabilization in which, like fly ash, you have and other substances that have calcium contents. They result in geopolymerization, isn't it? So this geopolymerization will form a stiffer matrix, and if you uh, mm, form they form that cash gel, Nash gel. So it will no longer be that particulate material that we are talking about. Do you understand what I'm saying?
Yes, madam. But my question here is, after adding the fly ash for the soil,
Okay.
how do you classify them? For example, fly ash, you are adding some 50% to the soil.
Hmm.
Again, are you going to give only the same IS code names? For example, GW or SP or SC or
I
something
don't
like
think
that only,
I
or
I don't think so. I think that the soil that you are using, you can classify that soil based on this IS classification, and then there must be a range of particles that you are using for soil stabilization. and then it will be your, I don't think that another particle size distribution is to be done after amending with fly ash, because it will be it's kind of a are you working in geopolymerization?
No, no, no. It's a general question I asked because
Okay, so
we study with
okay.
ground element.
Okay, okay. So you can, what you can do is you can mix, let us not say fly ash, because thought about geopolymerization, because geopolymerization will form matrices and then the material will not be as granular. So let us say that we have two different granular materials. Okay. Let's say we have two different
Done, madam.
granular materials that we are blending, and then we are
Hmm.
checking the IS code uh, um, um, index properties or the limits. I think it is kind of a standardization, and it is easier for researchers to follow. Uh, it will be easier for other people to follow your study and compare their results to your study if all of you are doing the same standard tests, isn't it? If you are doing a different test,
Okay, madam. Fine.
you
Fine.
understand what I'm saying? So if the two materials
Yeah, I
are not
understood, madam.
reacting with each other, the two materials are not reacting with each other, they are forming a third type of granular structure, you can definitely uh, do the sieve analysis in that, and then you can use the same properties here, but you have to then uh, discuss on what is the change in the properties that took place with your what you did. I hope that is clear. Am I
Done,
clear?
madam.
Okay. Okay. So then,
Yes, madam. Yes, madam.
okay. So after this gradation, we calculate the uniformity coefficient and the coefficient of curvature. The uniformity coefficient is kind of an indication of the gradation, if it is well graded or poorly graded. And then we have for the soil that has passed through the 75 micron, you do the uh, hydrometer test. Okay, you do the hydrometer test. So in the hydrometer test, what we do is, I'll just tell you the principle of the hydrometer test. We homogenize. When we want to calculate the uh, number of particles, the percentage of particles of different uh, diameters. So here we just used a sieve, but here we cannot use a sieve because the particles are very small and they have this tendency to coagulate and flocculate, and we cannot know the true size. So what we do is we say let's let the particle be spherical. Okay. So what we do is we say let the particle be spherical. First thing. Second thing is we say that all particles have same specific gravity. Your specific gravity is your uh, density of solids over density of liquids. Now this density of solids is mass of solids by volume of solids. So this volume we can assume from this sphere. say pi by 64 are, oh, let us say that this is the volume of the sphere. This is the thing that we want to calculate. So what we do is, if this is constant, then we can say pi by 64 R4 equals mass of solids over GS. Okay. So then what we do is we say that when settling down, this particle will achieve a terminal velocity when it is flowing through the hydrometer. All particles after some time, based on their mass, will achieve terminal velocity. Okay. So uh, based on Stokes law. So why this is important is because your Stokes law is dependent on the mass of your particle. It means that if all the particles have the same velocity, they have the same density, that means that at same height you will have particles that have same size also, because the specific gravity of the particles is same, the velocity of the particles is same. So at every uh, level you will have particles that have same diameter. Okay. So this is the concept that we try to uh, take advantage of. Then we take a hydrometer. Hydrometer is a device that tells you, that calculates, or that helps you measure the specific gravity of a liquid. So hydrometer is used for measuring the specific gravity of a liquid. What it does is, at its bulb, it will tell you what is the specific gravity of this layer. So when you know the specific gravity, and you know the terminal velocity, uh, so you can calculate the diameter based on this principle. So there are a lot of calculations, but the main logic is same, that all the particles will reach a terminal velocity. All particles have same uh, uh, specific gravity, the mass specific gravity. But when we talk about the specific gravity that the hydrometer is calculating, it is calculating the hydrometer of this solution. So it means that it is calculating how many particles of this material are in this solution. If you understand what I'm saying. So from Stokes' law, we will get the diameter based on the viscosity and the specific gravity of, and the velocity of the uh, this thing. We calculate the velocity, we calculate the hydrometer reading, time versus hydrometer reading. We can calculate the d. So these are the coefficients, or the index properties for coarse grained soils that we use. They are not used for fine grained soils. Fine grained soils have other properties, index properties. So for fine grained soil, we have consistency limits. So based on these consistency limits, we will define if the soil is silty or if it is clay. So basically, this is talking about this type of soil, and you, yes. So this talks about the state of soil. So what you can have, what it means actually. So what this means actually is, let us say that I took a soil sample which was completely dry. I took it in a container. This is a dry soil sample. Then I will start adding water. And as I start adding water, initially what will happen? Initially, let us say this was my state, completely dry. Okay. Initially, all the water that I am adding to this soil is going into the pores. So what will happen is there will be, if we talk about volume change, there will be, this is the water content. There will be no volume change up till saturation. Now that each and every pore of this material has been filled with water, after that, if I put more water in it, what will happen is we will have an increase in the volume. So the volume will start increasing as we add the water. So why this is important is, so this is a limit that is called the shrinkage limit, and then we reach something that is called the plastic limit, and then we have the liquid limit. So why we are talking about this is because the behavior of the soil based on the water content is very, very different. For example, if you have a clay which has a lot of water in it, like when it rains and then the soil becomes so slippery and you're just falling down and your foot is just going inside the ground because uh, the strength is not there. But if you go to maybe a very dry, arid area, maybe where it has clay soil, you will see that there are these cracks developed in the clay and it is as hard as rock. Basically, uh, had different water contents. So, because soil is a granular material, that is why the soil mechanics and solid mechanics are very different. We talk about solid mechanics, the steel will have the same strength if it is from that same, like, it's not going to change. But in soils, the strength changes based on the gradation, based on the water content, based on the loading history, uh, and all these things. So what this indicates is the shrinkage limit is the limit. We can say that this is the minimum water content for saturation. This is the minimum water content. See, soil after this is completely saturated, and below this, soil is not saturated. So we can say that this is the water content at which we can say the soil is saturated, and over and above that, soil is obviously saturated. Then we have a plastic limit. Plastic limit is like, in soils, the water content is, it makes soil workable. Like you think about the potter's clay, the consistency of that clay in which you can mold it, and it retains its shape. It's not so dry that it is crumbling. It's not so wet that it is sticking. That is the plastic limit. And then the liquid limit is like, liquid limit is the maximum water content, we can say, a limit to the water content, above which it hardly remains a soil. It becomes a solution of, it becomes a slurry, we can say. So these are the limits that we have defined for fine grained soils. And then we say that as the water content increases, the strength decreases. Can you, because dry clay will be very strong, and then as you increase, the matrix in the matrix, the the soil particles are getting replaced by water particles, and what um, so yeah, this is the stress and strain. Yeah, your water content is less than plastic limit, so you have, like, you are in this area. Okay. So you're increasing the water content and you reach this area. This is called semi solid. This is solid. This is semi solid. This is plastic, and then this is leak. This is solid. Okay. So you are in this zone, so you have a good strength stress strain relation. But at uh, plastic limit, but at liquid limit, if you have this much water in your soil, your strength will significantly reduce. And after liquid limit, we can say that the soil does not have any strength, because you see your stress strain curve is flat. So this is about how we calculate the liquid limit. This is through this Casagrande's apparatus. I'm sure you must have covered this in lecture, because I want to now go to some questions that we can do. Soil classification list first. Yeah, based on this plasticity index, which is liquid limit minus plastic limit, like this range. If the plastic limit was here, we will have a greater plastic limit. If the plastic limit was more towards the liquid side, we will have a smaller plastic. So a greater plastic limit will indicate that the soil is clayey. A smaller plastic limit will indicate plasticity index, sorry. A smaller plasticity index will indicate that the soil is silty. Because silt is like sand, it does not have cohesion. It is like a smaller version of sand. It will not show you plasticity. It is non-plastic, it is silty. If it is plastic, if you can mold it, then it is clayey. So plasticity index, if it is 0, it's non-plastic, less than 7, low plastic, 7 to 17, greater than 7. And then we have this chart in which we define if it is clayey or if it is silty. Yes, yes, Arav. A, yes, ARV.
No problem, madam. Can I ask you some questions?
Yes, no, no problem, no problem. I'm here for that only.
Okay. Yeah, there are two questions, madam.
Yes.
One is a general question which I have not seen till now anywhere. Do you have any source or textbook shows the fabric or structure of a soil in all the four states: solid state, semi-solid, plastic, and etc. In all the four states, do you have how the fabric differs? Any source gives answer for that?
I will have to check, because the source I have Uh, let's do one thing. I have some sources we can check.
Because I have used a number of books and etc. I have studied. So, the structure will come normally when you apply a force like a compaction and other things they have given,
Hmm.
flocculated or less flocculated or dispersed or something like that, single grain, whatever may be. But here, and this one, in all the four states, how the fabric looks, I have not observed anywhere. If you have gone through that, it will be fine. Structure or fabric, anything, madam. I have not gone through all the sources. Maybe in your research, if you refer anything,
Yeah.
if
What
you
I will do
right,
is
okay.
I will you give me your email ID.
Yes, madam. Sure.
You
Yeah,
actually what
madam.
I
I
will
will.
do, I will just write my email ID. You mail me, and
I
I
will.
will look for this source and I will email you about.
Thank you, madam. Thank you. And the other question is, yeah, I will note down.
Yeah, please. You can s underscore says
Yes.
at the rate ce.iitr.ac.in. So if you have any questions regarding the course, regarding the lectures or the interactive sessions, you can uh, like it
I will
is
use.
for everybody that you can contact me on this. Yes, please.
Yes, madam. Can you show me the previous slide, madam? That consistency limits graph. No, no, from your notes. From your notes, you have drawn.
Acha, my notes.
Uh, yeah,
Okay.
this slide, madam.
Yeah.
In this, normally for most of the soils, the sequence of the limits will be lowest one is shrinkage, then plastic, then liquid limit.
Yeah.
But do we have any special soils or some extreme soils where plastic limit exceeds the liquid limit or shrinkage limit exceeds the plastic limit, something like that? Maybe I have seen one question in either in IES material or it may be in Google search.
To be
Understood?
honest, I understood. I understood.
Yeah.
Uh, to be honest, what I can think of is that the most, uh, at most, what can be is like if this is your shrinkage limit
Hmm.
and this is your plastic limit, it can be very, very close to each
Close.
other.
Okay. Okay. Okay.
And then you will have a liquid limit, and then you will have a plastic limit, and it will be very, very close to each other. But
Mhm.
uh, what I can think is, I don't think that it is possible that
Okay.
we will have these in reverse order. And why I am saying that is because, first of all, if we talk about plastic limit and liquid limit, it is not possible for a slurry to be like, see, in both, in this case, what is happening is that the soil does not have plasticity at all.
Yeah, because narrow gap.
Narrow gap.
Clay
So,
content is
because
less.
you will just go to the slurry and just think about it, that you have added so much water that if you think about it in the perspective of, let us say, your wheat flour, if you
Okay.
put too much water in it, it will become mushy.
Mm.
You understand that? It is
Yes.
like this wheat flour, when it is dry, it will be solid, and then as you're going on adding water, there will be a state when it's the perfect time for the rotis. That's the plastic limit. And then you have we add more water to it, you will form a slushy, isn't it?
Yes,
So
ma'am.
but some Where the difference comes is that, for example, if you try to do the same thing with um, sand, sand will not at any point form that texture where you want to roll it and make a roti out, or it cannot be workable because it does not have any cohesion. This plasticity is inherently a property of clays. If even fine grained soil you are not able to roll and make plastic, it means that the soil is silty.
Yes, ma'am.
So, another question? Do you have another question?
Done, madam. Thank you.
Okay. Okay. So, these are the classifications. So, the classification can also be made based on relative density. The relative density is only for we only talk about relative density in terms of uh, coarse grained soils. We don't talk about relative density in terms of fine grained soils. When we're talking about fine grained soils, we usually talk about compaction properties. We talk about maximum dry density and optimum moisture content, which will be covered later. So, this is something that we talk about in coarse grained soils. Why? Because in coarse grained soils, because there is no cohesion, majority of the properties are determined by the size of the particles. Majority of the properties are dependent on what's the size of the particle versus the size of the voids. But for clay soils, it is different because of the cohesion. Okay, so this is like, so you have a sand. I take it from the field and I uh, loosely pour it in a mold. Okay, so I'll check the density when I have loosely poured this, and then I will put this on a shake table and I will vibrate it such that these particles will slip and fill the voids. What will happen is that after vibration, your particle will attain a denser state. Until now, the particles were something like this, but after shaking, they will kind of um, fill all the voids possible, not all of them. So we will get a dense state. Then we will check the density here. So density here is inversely proportional to the void ratio. Based on this is the loosest state possible for this soil, this sand, and this is the densest state possible for this sand. And then I'll go to the field and I will check what is the void ratio of the soil there. And from there, I can understand that based on its own capability, on the property of the soil, what is the minimum void ratio it can have, what is the maximum void ratio it can have, where does its natural state right now, what does it tell me about the soil? Is this a loose deposit? Is this a dense deposit? So it talks about relative density. Like, is this like this is the distinction you will make when you talk about loose or dense soils. Loose or dense soil is not only dependent on what is the void ratio of the soil, but it depends on what are the limits of void ratios for this particular soil. Okay, then we have the classification. Okay, so what we can do now is we can move on to cover some questions. So following are the results of a sieve analysis, and form the necessary calculations and plot a grain size distribution curve. Determine the D30, D10, D60 from grain size distribution curve. Calculate the CU and calculate the CC. Okay. So let me open an Excel sheet. So is we will copy the data here. After this, what we want to do is we want to calculate the cumulative mass returned. This will be mass retained. This will be this plus this. Are you following me?
Yes, ma'am. You can slightly zoom it, madam.
Um,
At
okay.
the bottom, at the bottom, you can zoom. That's enough, madam. Thank you.
Is this okay?
Yes, madam.
Okay. So cumulative mass. Now we will check percentage finer, or this is the mass retained. This is the cumulative mass, and then we have the percentage retained, which will be our total minus percentage mass retained. This will be our cumulative mass divided by into 100. Okay. Okay. Then we will have percentage finer. Percentage finer than. This will be 100 minus percentage retained. Okay. So what we did is we took all these sieves, we stacked them one on another, and then laboratory process is that first you weigh the sieves, and then you take the sample, let us say 5 kg, 1 kg, 2 kg, particular uh, a particular mass you take, and then you put it in the sieve and then you shake. Either it's an automatic shaker, it can be a manual shaking also. After that, you weigh the sieve again and then subtract the weight of the sieve to get the mass retained. This means that out of, for example, 2 kgs, 21.6 grams were retained on 2 micron, which means that it does not mean that 2 micron, sorry, 2 will have 21.6% uh, of the particles will be of 2 micron diameter. It just means that uh, no no particle, this cumulative, let us say 45, 425 micron. This means that 173.7 grams of uh, the total soil we have taken, this much soil has a lower diameter than, um, has a higher diameter than 425, that is 425 micron. That is why it was retained. And here we are subtracting 100 because now we are saying that 100% of the particles are smaller than 4.75 mm. 95% particles are smaller than 2 mm. And then what we do is we plot the particle size distribution curve. So the particle size distribution curve will be, X will be your sieve size and Y will be your percentage final. Okay. But you know that the X axis for this graph is on a log scale. Okay. Just a moment. Let us take 3 cycles. Okay. Taking percentage final. First of all, this is always up to 100. It cannot be greater than 100%. I think it seems to be the issue.
Why you selected pan, madam? Pan is not a diameter. Pan is not a size,
Okay,
no.
okay. That is why I'm having the
Yeah,
issue.
yeah. Now it is okay.
Okay. Yes. I was thinking what's wrong with the graph.
Right.
Okay, so this is the graph. Now what we want to do is we want to select the D60 and D10 and D13. So what we can do, something like this.
X-axis you can take a minor grid also, madam. It will
Hmm?
be easier. X-axis you can add a minor
Yeah, yeah, I will do that.
lines.
This I think we should have 10. Oops.
Yeah, it is visible, madam. You can count at the bottom.
60. This is point 1, point 1, point 2, point 3, point 4. So we can say that D60 is 0.4 mm.
Millimeter.
Then let's do this for D10. And be like 0.09. This D10. Now let's do D30. D30.
Point.
0. Point. So CU is equal to D10 by D60, isn't it?
Yes, madam. 4.44.
D10 by D60. D60 by D10. Let me check. D60 by D10. Then we have a CC. which is d30 square divided by d10 into d60. So it will be 1.11. Is that correct?
Yes, madam. It's correct.
Okay. So based on this, what can you say about the gradation or uh, the classification of the soil?
I think SW.
So first of all, let's see where is our the limit 4.75. One second. One, three. We can say that this is sandy because it hardly has any gravel. Then for sands, yes, greater than 4. Yeah. So the classification will be here. So what we did the calculations. We determined these terms, calculate the uniformity coefficient, and then we calculated the coefficient of curvature. So your CU equals 4.44 and CC equals 1. Okay. So next question is, following are the results of a sieve analysis and a hydrometer analysis on a given soil. Plot a combined grain size distribution curve. Plot From the plot, determine the percentage of gravel, sand, silt, and clay. Okay, so let's take this. So this is the hydrometer analysis. This is the sieve analysis. Let's say this is the sieve analysis. Then we have the hydrometer. This is the hydrometer analysis. Three, 16. see 16. Sections mm, mm. So what we can do, what's happening here is that at the transition of, like, when we are going from here to here, we see a slight increase uh, in the dia. That is because, like, you're transitioning from one kind of analysis to another kind. So what we will do is we will take a moving average here, or uh, in this case what we can do is, it's a good practice to, uh, what you can do is you can leave out the faulty result, but at the same time uh, you can still show the outlier in your data. Let us use a different type of chart. Take this reading. We can do both things. What we can do is we'll take one graph, say graph one. One, we will remove this reading, and in graph two, we will remove this reading. Did I take the pan again? Second. Just a moment, my mouse is not working properly. Change chat. This is what I was looking for. We will have scatter. Mistakenly copy pasted this several times. Okay, so these are the graphs. Okay, these are the two graphs that we have. Let's say this is graph one. This is graph two. Here we will also add because we have deleted the 0.8 point. So we will add 1 point. X value will be this. Y value will be this. So we can say outlier. Okay. So this is our grain size distribution curve. If we skip the uh, point 8 and then we have a grain size distribution curve and we will add the x value for 0.75 here. It's just below this. blue part. Basically, this is just to show you that it's always good practice to show all of your results, but the outliers and everything you can still show. So the next part of our question is plot a combined grain size distribution from the plot, determine the percentage of gravel, sand, silt, and clay. So for gravel, we will make a distinction at 1, 2, 3, or at
0%.
20 at 2 mm.
You're searching for gravel, na, madam?
Yeah. So at 2 mm, we make the distinction for gravel.
Why, madam? It is above the 4.75, na?
I think 4.75
Above is
is,
gravel. That's why it is in the table also you can see 4.75.
yeah,
Passing is 100%, written is 0.
3.7.
Even in our table also we can see, madam. Gravel
Yeah.
easily we can see from table.
Then we have sand, which is from 4.75 till
Up 75 microns.
0.32567. 55 microns. Okay. So then we will have, but
75 to 2 microns.
0. Hmm. So basically, what we will have is something like this. At 0, but this- yeah, hmm, this is what I want to show. So greater than this will be our sand till here. This will be 1, 2, 3, 4.75. 1, 2, 3, 2.75. This will be all sand. Below this will be gravel, and this will be silt. Here's the 75 micron, yes. Just a moment. They should be up till 1, 2, 3, 4, 5, 6, 7, 8, 8. It's total here. And then we have silt from here up to,
2 microns.
yeah. So above this is gravel, this is sand. Mhm. Silt color. This is silt. So what we can do is we can do the next question. Okay, so this is the question. Let's move to the next question. Following are the results of a test conducted in the laboratory. Determine the liquid limit and the flow index. Okay, so liquid limit. So in liquid limit and flow index, what we do is we plot number of blows against the water content. X axis is the number of blows, y axis is the moisture content, and the x axis has to be in logs. temperature axis of 5. Acha, the techniques. Let us say it's 10, it's 20, two. This is like 39.9 limit will be 39.9. Is that fine?
Yes, madam.
Let me do one thing. Let me add Axis titles so that when I share this in the content percentage, this is the legal limit question 3, this is question 2. Let's add the Axis titles. This is the calculator. This is percentage. Size is Axis titles. This is the percentage finer. This is the parameter. This is size distribution. This is question number 1. The next part. Okay. Following are the results of a shrinkage limit test. Initial volume of soil is given. Final volume of soil in dry state is given. Initial mass in a saturated state. Final mass in dry state determine the shrinkage limit of this.
Madam,
So
not visible, madam.
now is it visible?
Little bit, madam, little bit. Some more.
But this is on the entire screen. Are you not able to see this?
Yeah, it's okay, madam. Better.
Okay. So as we as we discussed earlier, that shrinkage limit is the minimum moisture content for saturation. Just a moment. I think somebody. Okay. So the shrinkage limit is the minimum moisture content for saturation. So if we take a representative element volume, we can say REV here, it will have this is called the um, three-phase diagram, in which we have a solid part, then we have a void, we have the voids. Voids can be air voids or it can be filled with water. So this is the volume of solids. This is the volume of voids. Okay, this is the complete volume. Usually we take it as one when we are defining these relationships. I don't know where it went. There used to be this tab in which there were these pen commands. Just can't seem to- Okay, I'll have to check again. So we want to calculate the shrinkage limit. What we want basically to calculate is this void ratio, this volume of voids, which is the minimum water content required for saturation. So this is the saturated state for this V, and what we do is first we calculate the weight and volume of this unsaturated state. Then we take the dry state, and then this is basically what we are calculating, showing. So यहाँ से ये लेके आऊँ इरेजर. Okay. So this is the initial volume of soil in a saturated state, which means that this is V1, saturated state. Let us say this is V1. The final volume of soil in a dry state, which is this. initial mass in a saturated state. This is, so let us say that this was the mass of solids. It will be same all throughout. Okay, and this is M1. Final mass in dry state. This is M2. So here we are not able to calculate only the mass. We will always have some kind of water with it. But here, because there is no water, the mass that we calculate here is actually the mass of solids. So this is M2, this is M2, this is M. Okay. So shrinkage limit will be the water content here. Water content is volume of voids. See, we can use the equation if we want. It is easy to just put any equation there, but just so that you get a feel of uh, what we try to do, and you get an intuitive idea of what we are doing and why we are doing it, and that is why we are trying to calculate it from a basic principle. So water content is volume of what is sorry, weight of water by weight of solids. Weight of water by weight of solids. And at this saturated state, this is the shrinkage limit. Sorry, you see the saturated state. You took a soil, then you saturated, but you don't know the minimum amount of water for saturation, so you have gone above that. So this is the one state that we have, which is greater than water for saturation. And then we took the volume and the mass measurement of this. Then we dried it completely. Then we took the volume and mass. So this gave us the um, now what we will try to do is we will assume that the mass and volume of solids is fixed, and we will try to interpolate uh, uh, interpolate the shrinkage limit from these two states. So this will have water content greater than Ws, this has water content less than Ws, and this has Ws, isn't it? So uh, what we will do, I hope this is making intuitive sense. Is it? Is it making sense?
Yes, madam.
Okay. So what we want is to calculate this volume and then subtract it from this state. So we can say this is V1, this is V2, this is M1, this is M2. Water content here will be M1 minus the total water here will be the total weight minus M2, this minus the weight of solids, This will be the mass of water divided by mass of solids, which is M2, water content here. And what we want is, this is WL, sorry, WS. WS equals, let us say, mass at shrinkage limit minus M2 divided by M2. And we can say that this is equivalent to this whole mass M1 minus M2 times minus gamma W times this volume, let us say VI. So this is the final volume and this is the initial volume. We can say this is V initial minus V final. Can we say that? So now you got this volume. You just have to multiply it by density of water, subtract this portion from here. You will get your state, your saturated state. Do you understand? So did you
Yes,
follow?
madam. It is nothing but the loss of water from the initial state to the shrinkage limit.
Yes, yes, exactly. So
Yeah.
what we are trying to do with the formula, I'm trying to give you an intuitive idea about the formula. What we are trying to do is we calculate this volume, which will be V initial minus V final, and then we subtract this mass from this, like we try to subtract this mass from this state, then we will come to the saturated state or the shrinkage limit. Then the liquid limit here will be our water content or your shrinkage limit. And that is what we try to do in this. Okay. The results of a particle size analysis of a soil are as follows: percentage passing through number 10, number 40, number 50. So, what you can do is you can try this question. I will be uploading the the PPT of this class. You can try this question, and this question I put because I wanted to discuss that sometimes the sieves are numbered, and you can have a US numbering system, yeah, IS numbering system. So you have to know some of the sieve names, like sieve number 4 again. So these are the sieve openings. Sieve number 4, what are the openings? Some of the sieves you should know. What is sieve number 100, 200, 4, 10, 40? So you can uh, uh, try this question. Try this question. I think what we will do is, yeah, we can continue in the next lecture with these questions. Okay. I think that is it for today. Any questions? Are there
Madam, one or two questions you can leave us so that we can solve it along
okay?
with the answer, along with the key only.
Uh, yeah, what I can do is I can do is you can if you are not able to solve the question, you can mail me. But if I leave you a question, then I will be discussing it in the next lecture.
Okay, madam.
Okay?
Okay, madam. Yeah.
Okay, ma'am.
Are there any questions?
Madam, in professor's lecture,
Huh?
in week 2 beginning,
Okay.
he discussed with the phase diagram and details,
Uh-huh.
in which he mentioned the wide ratio range is 0 to infinite. But he said it is a theoretical. Where we are using that? Wide ratio cannot be 0.
Yeah, wide ratio cannot be zero.
At the same time, it cannot be infinite also.
Yeah, but you have to give a range, na?
That's okay, madam. But without knowing which soil will have infinite wide ratio, which soil will have a 0 wide ratio, why we
For
have to discuss
example,
0
for
to infinite?
example, let us say, for example, if I say that the void ratio, I can say that the void ratio uh, usually lies between 0.1 to 0.
Yeah,
To
yeah.
2.5. I
That
can say that.
yeah,
But
that means
what,
it's greater than 0.
yeah, so we
Maybe
by
yes.
Vs, isn't it?
Yes,
So
madam.
theoretically, what, 1 second.
The
What
wide
it's
ratio
saying
of
is
0
E
indicates
is
wide
greater
ratio.
than 0.
Yes,
It
madam.
cannot be 0.
Yeah, but he has
E
given 0 to infinite.
is greater than 0. Because if it becomes 0, then your soil stops being a particulate material.
Yeah,
Then it
it's
is a pure solid.
pure solid or impervious.
No, pure solid it will become.
Hmm.
Impervious, we talk about rocks. We can say that this is an impervious because the permissivity or the permeability is too low. But at the same time, rock still is a porous material. And that is the difference between a solid and soil, is the presence of voids. If you say that there is no void, that means that your atoms are connected like that. You
Yeah,
don't
check,
have
madam.
any
Check
void.
this. Check this and answer it, madam. From which source he has given 0 to infinite?
You can mail to the professor
Okay.
if you have a question about it, because I will not be I don't think I'll know about, because I am
Okay.
allotted this course through NPTEL, and
Understood.
direct interaction with professor is not uh, mm, like it's not available.
Hmm. Okay, madam.
Okay,
Thank you.
thank you. Okay, that's it for today.